Okay, good afternoon, good morning, good evening. So thank you very much to join this second IEEE Sequencing System Society Rio Grande do Sul Talks 2021, also in collaboration with the Federal University of Porto Alegre, IEEE Sequencing System Society Rio Grande do Sul Talks 2021, also in collaboration with the Federal University. So today we have the pleasure to have the talk by Professor Hai Li from the Department of Electrical and Computer Engineering, Duke University, USA. So Helen is Claire Booth Lucy Professor and Associate Chair for Operations of the Department of Electrical and Computer Engineering at Duke University. So she received her baccalaureate and master from Tsinghua University and PhD from Purdue University. At Duke, she co-directs Duke University Center for Computational Evolutionary Intelligence and NSF IUCRC for Alternative, Sustainable and Intelligent Computing. Her research interests include machine learning, acceleration, security, neuromorphic circuit and system for brain-inspired computing, conventional and emerging memory design and architecture, and software and hardware co-design. She received the NSF Career Award, the DARPA Young Faculty Award, the TUM IAS Hans Fischer Fellowship from Germany, a late fellowship, 8 Best Paper Awards, and another 9 Best Paper nomination. Dr. Lee is a fellow of IEEE and a distinguished member of ACM. For more information, you can reach her website that you can see here, the address. So this is just a very brief resume of Helen's CV, that besides she's still a younger professor, she has a lot of achievements and doing a very interesting work. And thank you very much, Helen, to provide and accept to give this talk today in a very inspiring subject. So thank you very much. The floor is with you to start your talk.
Thanks a lot, Ricardo, for a very kind introduction. And thanks to everyone being here today. I'm Helen Lee from Duke University. So today I'm going to give a talk related to the efficient deep learning net scale. Let me jump into the details over here. In fact, I'm going to give a very short introduction today, because everyone perhaps talking about the artificial intelligence, deep learning, deep neural network, and so on so forth today. One important trend during the exploration in this field is we tend to obtain better predictions. And the way to achieve this goal is to using larger models. So here I given 2 examples. On the left hand is the example of an image classification on ImageNet. Each circle here represent a model and the area corresponding to the model size. X-axis is the operation numbers in giga operations, and a y-axis represent the top 1 accuracy percentage. The higher, the better. So as you can see, if you compare all different models, especially if you do the comparison along the same series, like Inception series or ResNet series, when we tend to have better accuracies, and the model has to be deeper, larger, and it involves more computations. Similar observation can be obtained for language models. Here, the x-axis is the computation cost again, and y-axis is the test perplexity. The lower, the better. The trend over here obvious. In order to improve the language modeling processing, we kind of also extend the model size. So what is the problem of larger models? Okay, I guess many of you perhaps already have experience in training models. Okay, with larger model, more parameters, and then the operation, the computing time for each round is longer. And then larger models and usually is harder to get converged, meaning it requires more epochs during the training. And furthermore, larger models actually involve more hyperparameters. So, tuning hyperparameter is always painful. Basically, training larger models is a lot of slower, and it's also involved longer research and the production cycles. How about in inference? So I talked to Professor Ricardo here like a couple minutes ago and talking about the use of the deep learning models in IoT in inference. So as you can see, bigger models and requires a longer execution time. And for majority IoT applications, they are time critical. So longer latency definitely is in concern. Beyond that, at the edge, usually they have very limited compute and memory resources. So deploying large models to these applications is kind of a very, very difficult. So considering this in the past few years, and our lab has been working on how to improve the efficiency in DNN inference and training process. Okay, basically we explored different approaches. For example, at the conventional architecture platforms, and we conducted research at purely algorithm level, like the deep Hoyer work. We also consider how to rebuild models so that it's more friendly to hardware execution. Our lab also tend to explore the new architecture solutions. Maybe you know that we have been working on RM-based neuromorphic designs for more than 10 years. Beyond this, and we're also considering, hey, any software and architecture solutions in order to improve the training efficiency. Okay, so AgPar is one of the case studies I'm going to present. All right, so let me move to the details of those individual case studies, and I will start from deep Hoyer. The deep Hoyer's full name is an differentiable and scale invariant sparsity inducing regulizer. So as you can see, this is a pure algorithm level improvement work. And the goal over here is to induce a sparsity on DNN models. So basically for weight 0, it doesn't involve any computation, right? Any operations with 0, it doesn't change much. And then a very important research line in DNN acceleration is increase the sparsity, meaning made more and more weights to be 0. Okay, so to induce sparsity, previous research tend to utilize an sparsity inducing regulizer. You may heard about L1 regulizer or L0 regulizer. The figure on the right hand shows the contour and the gradient direction of those two regulizers. This is for L1 and this is for L0s. So if you're looking at L1 regulizer, it's differentiable and convex. So it is, relatively speaking, it's easier to optimize. However, the L1 regulizer is proportional to the scale of the parameters. Okay, so it can only scaling down all the parameters with the same speed. And this is why in this gradient maps, as you can see, this is kind of coming along these directions, right? This will lead to penalty on large elements in the weight. Basically, our general understanding is in large weight going to have a more impact on the overall performance. So during the sparsification during the sparsifications, we tend to maintain large weight and make a smaller weight to be 0. Okay, so this trend, in fact, is not favorable. How about L0 regulizer? L0 regulizer kind of directly reflects the sparsity because its definition is the number of the non-zero values and try to make it to be 0, right? So, but the problem is that it's a skew invariant. So L0 provide not useful gradient. If you're looking at the gradient over here, it's either infinite on the x-axis or 0 everywhere else. So it cannot work directly with the gradient descent method, which is very popular and useful in training process. And so in trainings, and we usually need additional tricks like stochastic approximation, ADMM during the prunings. So in other words, the optimization is a lot of more complicated. Okay, so what we proposed over here, we propose to move beyond L1 and L0 and to find we call sparsity inducing regularizer that is both differentiable and also skew invariant for DNN pruning. Okay, so one thing draws our attention is the Howyer regularizer. So I actually defined the Howyer regularizer over here. It is the ratio between the L1 norm and L2 norm. What we find is for element-wise DNN prunings, and we can propose to apply squared version of the Howyer regularizer, and we name it Howyer square. Through this and figures, it can be seen that this regularizer actually is differentiable. It's also skew invariant. So it has the same range and similar minima structure as L0, while the minima is achieved as 1 when only one element in the weight is non-zero. So Howyer square regularizer, we basically can consider as a differentiable approximation of the L0 norm. Okay. In our work, we further extend Howyer square regularizer to structure pruning settings. And the idea is very similar as in group plus cell. We apply Howyer square regularizer over L2 norm of each group of the weight. So represented by WG over here. So the weights within the group will be induced to become 0 simultaneously. And the selection of the groups can be along the channels or the filters. And in this way, we are able to induce structure sparsity in the model. Okay. I will not spend time on a lot of the details and just here to show some basic results. So as you can see, here is the gradient of the Howyer regularizer. And if you observe that, you may see that the gradient of the Howyer square regularizer with respect to each elements, there's a subtraction term. And this is induced what we call the auto-trimming effect. What does that mean? In fact, this figure kind of explains this. In this figure, x-axis represent the training epochs, and y-axis is the absolute value of an individual weights. And each curve corresponding to one weight parameters. We sample 100 weight parameters and for illustration purposes. So for those in smaller weights, okay, it's induced to 0 quickly. Well, for the weights with the larger values, in fact, it's a maintain. It could be also amplified. The dash line over here kind of indicating the auto-trimming effect and the threshold for it. It's gradually increases, so more and more weights will be induced to the 0 until we kind of reach to the certification of the performance. Okay. Very simple results to represent over here. For element-wise sparsity, the proposed Howyer square regularizer can further improve the model compression rate from the previous models without much accuracy loss. And for the layer-wise, the compression, you can see that Howyer square regularizer is especially effective for compressing the large fully connect layers. And as you know, fully connect layers are often the most memory intensive layer in deep learning model. Okay. We also test the group Higher square regulizer on compressing ResNet, which is very, very popular right now, right? So it's achieved the best trade-off curve between accuracy and number of the flops, and the trade-off points achieved by our method after performs the Pareto frontier, like the dashed line over here, composed by previous method. So generally speaking, we verify that our method can achieve both less flops and higher accuracy simultaneously. Okay, so as you can see, I only briefly introduce those methodologies, and if you're interested, then feel free to reach me, and I actually can provide more details. So higher work is a pure algorithm solution, as you can see. So in current research, people also wondering for DNN model designs, in order to improve the accuracy efficiencies, do we have to considering like the hardware mappings? Okay, so pennywork is also kind of the efficiency improvement through prunings and through compressions, but here the focus is made it more easier for hardware executions. In fact, there are a lot of different compression methodologies has been studied. For example, the compact model design, DNN model designs. For example, we can quantize the weight and activations from floating points to fixed points and to only a few bits. Through such kind of reductions, the computation cost can be reduced. I also introduced the pruning and the sparsification just now as by using Heuer as an example. Decomposition, for example, low rank approximation is another threat in the research. Its basic idea is to decompose large matrix operations into many smaller ones, like two-step smaller ones in order to improve the efficiency. So Penny framework is trying to combine these different approaches and having an integrated solutions. In Penny framework, we built the entire processing and the training into 4 steps. Okay, we will start with original kind of an kernel and channels and do the kernel decomposition. So in these steps, we utilize the low rank approximation approach. Okay, and afterwards, we start at about the sparsification and the prunings. Step B is an alternative for retraining. It's essentially a sparsity regularization processes. And C is an unstructured pruning, and D is in structured pruning. Let me give you some details over here. Okay, so that's taking a look at the kernel decomposition first. In fact, this is the most complicated step. We in fact start with a group of filter tensors. So each of the tensor has a kernel size of a KL by KL, and the channel size is in CL. Okay, and we have in CL plus 1 filters over here. So during kernel decompositions, and first of all, we unroll along the input and output channel dimensions, and then each row of the weight matrix will be represent 2D kernel. So as you can see, each row over here will represent this in KL by KL 2D kernels. And then vertically, there'll be CL times and CL plus 1 rows in this weight matrix W. Okay, so starting with this very large weight matrix W, we will conduct the decomposition. So essentially what we do is similar to principal component analysis and PCA approaches is we conducted a singular value decomposition SVD. So represent DW with a U, sigma, and we transpose over here. And through this processes, we can select the first k column vectors from U this with the largest eigenvalues. So those K entries can be reconstructed as a basis matrix. So compared to the original weight matrix, the basis matrix is a lot smaller. Okay, how about the remaining sin? We then project the original kernel with U and U transpose to form the we call coefficient matrix. Okay, so K actually is a very small number. So the size of this is also a lot smaller than W. But more importantly, this coefficient matrix, in fact, is very, very sparse. And therefore, we can apply the sparsification and pruning techniques afterwards. So with those techniques, okay, we reform this and reconstruct them to basic kernel coming from basics matrix and coefficient kind of coming from coefficient matrices, okay? So through doing this, and we only apply the basic kernels into the input feature map, okay? So let me move to the next step. Quickly comparison with the previous and some decomposition works. For example, Zhang Xiangyu's work back to 2018, and they decompose the filters and divided it into 2 steps. So this in 2-stage matrix multiplications, and it's kind of having each of them is smaller, but it's still 2-stage multiplications. So after data input feature go through the first step, we need store those intermediate feature maps and then make it go through the second step. So the real hardware execution, in fact, takes a longer latency. For our cases, in fact, we only need to go through this and smaller number of the kernels as in convolutional operations. The second step, in fact, we actually can stream the accumulation along the upper dimension. So it doesn't require us to store those intermediate information. It doesn't require intermediate buffer. Okay, so the question here is, and how can we do this, right? So let's keep this in questions and let me finish the step B and C. Okay, during the trainings and at the B step, we restore original 4D tensor, and then we tend to alternately train the basic and also coefficient. Okay, so we do that alternatively. And in step C, we apply L1 regularization to the coefficient to make it very, very sparse. Okay. And then on step D for model shrinkings, okay, I mentioned about go through the 2D kernels, a series of 2D kernels, and then the output intermediate feature maps will go through this and coefficient matrices, right? And I mentioned that we in fact do not have to maintain or keep those in intermediate results. Why and how? In fact, this in coefficient matrices can be partitioned as the output filter and the input filter, the output from the layer 1 and the input from the layer L+1. Since the structure over here is very sparse, and then PO and the PI over here, many of them in fact are zeros. So the output from layer L through those series of 2D kernels will go through this in orange portions. Anything 0 here, we do not have to do anything, right? And any data go through the blue one. If there's any zeros, we don't have to do anything. So by combining the 2 filters, we actually can remove the entries, either 0 in orange part or the 0 in the blue part, and made it even more sparse. This is how we kind of stream the data from the small number of the K kernels and through such kind of a filter, and we do not have to maintain the intermediate results. Okay, and the training processes, in fact, we can take the iterations and eventually made it very sparse and efficient. Again, experiments, it's very, very simple. and more details can reference our paper. For example, we did a test on Cepher 10 and ImageNet. The number of the operation reduction is very high. Basically, we only need about 10 to 20% of the computation cost as the previous versions. And if we looking at the Pareto line over here for pennies, and the accuracy is always better than the previous approach. Okay. We in fact did a lot of different experiments in trying to finalize, for example, the rank of the decomposition required. So, for example, the number of the basic kernels in K. What we find is when we have an 8, 7, 6, 5, in fact, it's only have a very marginal accuracy loss. And if we further reduce that to 4 and below, and obviously the accuracy loss is higher. And the number of the basic kernels, and the selection is very important because it's directly related to the reduction of the parameter numbers and also the computation cost in terms of the floating point operation numbers. Okay. All right, so the previous two examples I represent over here, as you can see, they are focusing on the conventional architectures. So our approach majorly is through the algorithm DNN architecture redesign or optimization in order to improve its execution efficiency. We, in fact, has been working on new computer architectures, and RAM-based neuromorphic chips is one of our research focus. If you ever heard about for example, RAM or memory stir, this, we say that it's kind of a rebirth of the neuromorphic circuits. It's a 2-terminal devices. Usually we apply the voltage across the device, and if the voltage or current of the applied, a voltage current exceed a certain threshold, we are able to change the resistance values. And this resistance value will sustain after removing the external excitations, right? So we can use this and wait for the weighting functionalities and related to or mimic the biological synapse function. More importantly or interestingly is at processing levels, people are able to making what we call the memory stir crossbar structure. Basically, we have a horizontal wire and a vertical wire and kind of an interwave like the picture show over here. And the cross points of the horizontal and vertical wires, at this cross points, and we can build one memory stir devices. So the structure cannot be represented as the circuit schemes and over here, right? If we apply the voltage and simultaneously horizontally and collecting the current at the vertical points here, it's essentially in matrix operation. I mean, ideally without considered non-ideal situation, it's a very nature matrix operation. And this is the, represent a large volume of the synaptic weighting functionalities. And this actually the start of our research along these lines. And later on, as you perhaps know that many people explore different design approach. For example, the data can be represented by spikes. This way is closer to biological systems and offer very, very high power efficiency. In fact, our original study is using analog voltage. This way is, with the assist of the DAC and ADCs, it's still compatible to the signal processing in current designs. It's faster. The drawback, in fact, is in the design, particularly of the ADCs, is very costly. So, for example, for spike-based and neuromorphic designs, if we apply the spike as the input data and collect the current, made it go through integrate and fire circuits I have seen over here and generate the output spike. Okay, Ideally, I mentioned that the expectation is the output spike number shall be proportional to the weighted input function. Okay, so it shall be kind of a linear functionality. Our simulation and also the later on testing with the real chip shows that it's not like a perfect linear functionality, but kind of with such kind of a shape. Okay, so in real computation results, what we find is, first of all, is constrained by the FC operation speed, and second, if you're looking into the details, and there's small variations in terms of the output pulse generation. This is related to the non-ideality like capacitance and resistance and in crossbar arrays. Okay, so this is the real situation we have to face. In fact, in our labs, we integrate such kind of a non-ideal situations into our model training process to ensure the performance. So I mentioned that we actually start the research along these lines since 2009, and it's been more than 10 years. And we have tape out a few chips and for different designs and tend to improve this and continuously. In fact, in 2019, we have this in spiking versions, and today's research part or technical part is majorly based on this. So our latest chip design, in fact, is a spike-based. Here I represent the spike conversion circuits. We actually use the output of the op-amp to form a positive feedback in order to accelerate the response of the current amplifier. We also use the current measure to scaling down the baseline current, because in real neural network applications, the result current can be pretty high, depends on the array size, right? So the peak baseline current could be very large, and therefore we need to scaling down when processing this data. And of course, in the current amplifier, C drives bit line and source line, drives bit line, and the source line will sync current by connecting to the ground over here. So the op-amp here is used to stabilize the read voltage by virtually short the bit lines to the ground. And then at last, and as you can see in our designs, we have an additional phase compensation because in the designs, and there are two positive feedbacks. One is on the op-amp, and another is the FC positive feedbacks. So it's made stabilization harder. So we have to adjust the pole of the entire circuits and from the perspective of control theories. The right-hand side here, in fact, is the simulation results. CA, it shows that the input current range from like 10 microseconds, 10 microamperes to like up to 1,000,000 microamp. And as you can see it over here, with proper phase compositions, the response actually can be quickly converged to the stable state. Okay. This is our simulation results. So in those designs, we propose a very important concept we call in situ nonlinear activation function. So in neural network processing, as you can see, usually we separate matrix multiplication and from the nonlinear activation functionalities and use two steps for operation. In our designs, and since IFC is integrated with the crossbar array operations, and so we combine them together to simplify the processing element operations. So when we are doing this at circuit levels, this is the same circuit I just presented. We need some knobs to tune and during the operations. So VREF of the current amplifier is corresponding to or clamp the read voltage for the bit lines. So when we increase this, the bit line current can be increased. So it's provide proportional tunings. The threshold voltage here for the FCs, and this is the threshold for the capacitance charging and discharging. So if we reduce the threshold, it's made charging and discharging more frequently. Okay, so the right-hand side is the measured ISNA behaviors. Horizontal is the MAC computation result, and y-axis is the spike frequency. We tend to maintain our operations in this range, and this is kind of a corresponding to the linear region. And I mean, if the MAC result exceeding to kind of this range, it becomes to saturate. So this activation function is very alike of the click the ReLU or tangent functionality. Both are very popular in DNN designs. In fact, our work, we have very thorough explorations, and might not be able to jump into this in very detail. We have a fully integrated of CMOS and also RAM design, and this is an our chip die photo. This one corresponding to the testing data related to IFC only. So as you can see, when we change the input strength and then the output spike generation, its frequency changes. The bottom part actually shows in our testing results on different networks. Okay, I will just explain this one. So this one, the left bar represent ideal one, meaning what we obtained from algorithm, from PyTorch testing. And the red bars in here is the binarized, like the same network. If we do the binarization and made a way to be 0 and 1s, how is the performance? So through carefully training, and the degradation is very minimal, as you can see. Programs represents that when we program to memristor cross bars, because in those 1 and 0s will map to the physical values, right? So it's also kind of induce in certain performance degradation. Okay, so the observation over here is for very simple networks, and the degradation is large. But if the network is large enough, and the degradation is not much. And then the green one is measured result on our RAM chip. Compared to the green versus the blue, as you can see, the measured accuracy is very alike. It's basically matched to each other very well. Okay. So this actually present our recently, circuit and chip designs. We are quite confident on this line of the research, and looking forward to working on this and further as well. So very simple comparisons. We compared our work with the compute in memory micro designs, and also the P processing elements designs. The cell area is a lot of smaller than the others, and then we also show that our energy efficiency is a lot of higher than the others. Excuse me. So with such kind of a new architectures, and meanwhile, we also tend to explore how can we extend its utilization efficiency in inference and also in training. ACPAR is talking about the tensor partitioning, and over here we focus on the training efficiency. I mean, in this work, we particularly focus on tensor partitioning. So why tensor partitioning? This is because tensor is the basic data unit in deep learning operations. So in deep learning training, for instance, it has a forward path. So during the forward path, what we have is the input feature map of layer L will go through the weight matrix of layer L and generate the output feature map FL+1, which will be used as an input feature map of the next layer, right? And then the backpropagation path, we actually use the arrow generated by layer L+1 multiply with the weight matrix L, the transpose of the weight matrix WL to produce the arrow matrix of an EL. Okay, and the gradients calculations is also related to FL and the EL over here. So here we denote the tensor with the same shape and then made it by one simple for easy understanding, for simplicity of the understanding. So essentially we have three shapes, A and B and C, A corresponding to the shape of the input feature map, B corresponding to the weight matrix, and C corresponding to output feature map. And A and B and C, three types corresponding to one DNN layer. Okay. So now that's looking at the partition of the matrix multiplication. Okay. Talking about the one layer operations, and if we tend to divide it, partition that, and allocate it into two cores or two processing elements, what do we do? Originally, we have an A times B equals to C, A multiply B equals to C. So a row of the A will do operation with the columns of B and generate one entry of a C matrix, right? If we tend to have a parallel compute, so we divided a row of an A into two parts and separated into like two arrays or two PEs. So on matrix B part, the partition will along the column directions. So what happens is for this and two processing elements, each of them will have a partial summation. The green dots over here. At the end, we need to sum them together. Okay. So by observing such kind of operations, we find, in fact, we have three basic partitions. The basic partitions will align with the gradient operation, the forward operation, or the backward operation. For example, let's take the forward path again, right? If we partition, A array and getting this distributed into multiple PEs, and correspondingly, the B will partition along this ways, and then the shaded portions will be goes to the same processing elements. And then, as I explained previously, the two of green belongs to two PEs, and eventually we need to do the summation. So on back propagation path, the arrow produced by C, after we produce the full arrow matrices, and we need to work with the B. We kind of again distribute back to different P's and produce an A. And then for the gradient operations, again, the shade part belongs to the same PEs, and N shade belongs to another PEs. Okay. So in this, when we analyze the partition cost, okay, we evaluate it from computation cost and communication cost. Computation cost is the total number of the flops for the entire operations and divided by the number of the accelerators. And communication cost is defined by inner layer and interlayer cost. Okay. And the interlayer cost, in fact, is the majority contributions. So again, let me show you the partition cost, communication cost. So considering this part is layer L, and this is corresponding to layer L+1. Okay, so layer L, we partition this, and this part, the green part, belongs to two PEs. Okay, and then the F over here, for instance, will be passed to used as the input of a layer L+1, right? So as you can see that if we doing this, right, we actually transpose this to a next layer, and the generation of the error of the next layer on the back propagation path, and it will come back to the previous and green, like 2 P's. The interlayer cost with the cost for the tensor conversion from one layer to following layer or verse back. So over here, as you can see, only this small shaded portions contribute to the arrow arrays. In fact, we need kind of a lot of communications and through all the P's over here in order to get the whole set of the arrow matrices for layer L. Okay, so correspondingly, based on the 3 basic partitions, and there will be 9 interlayer communication patterns as I illustrate over here, and each of them will represent a different cost. And then during our designs, and we tend to decide for each layer, shall we config by type 1 or 2 or 3? And when we are doing this, and we apply dynamic programming approach to minimize the total partition cost. So we start from forward path and backtrace to determine the final decision. More than this, and when we design this, and we also have to considering the hardware arrange, right? The mapping of the P's. So in this one, we use hierarchical partitions to recursively portion on different accelerator groups. Okay, so very quick introduction of our results. In fact, the approach itself then can be used as any kind of a P structures, like the P designed based on RM arrays. In our test, in fact, were conducted on TPUs and TPU v2 and TPU v3s. So we have an heterogeneous designs like TPU v2 plus TPU v3s. We also have the version of homogeneous accelerators. Okay, so very simple. We compare this with the data parallelism, which only have a type 1 partition. We also compare this with the OWT, which have used data parallelism for convolutional layers and model parallelism for fully connect layers. And HyPar is our previous works, and we have data parallelisms, also model parallelisms, and so it's only considered type 1 and 2 and didn't have in type 3s. And so anyhow, and over here, as you can see, our new proposed ACPAR is apt to perform than the previous schemes in terms of the throughput, execution efficiency across all different DNN models. This is the result, is the performance on homogeneous accelerators, and I don't elaborate more over here. The last figure actually is the Alex partition type configuration. I would like to show a little bit. As you can see, for convolutional layers, early layers in type 1 is kind of a dominant, and when we involve fully connect layers, actually utilize in type 2 and 3 and more. But as you can see, it's kind of always the combination of different types can bring the best results. It's not like one single type can apply to all the layers and result the optimal results. So this is kind of a very interesting part we observed. Okay, so this is kind of again very rough introduction of our study on hyper. So in today's talk, in fact, I present different research, 4 research outcomes conducted by our labs recently. Generally speaking, and as you can see, we explore algorithm level, we explore the software and hardware co-designs, and we also kind of dedicating new architectures and circuits and to be proposed. What we believe is in order to have an efficient inference and the trainings, and we need a hardware-friendly solution in order to maximize the benefits of general software and hardware platform. So this applies to GPU solutions, CPU solutions. Non-conventional hardware architectures and becomes more critical. I mentioned about ARM-based designs. In fact, accelerator design have many different varieties already. We also kind of export systolic like TPU designs as well. Anyhow, a holistic scheme that integrates device circuit architecture, algorithm, and even application-specific designs and becomes more and more interesting and necessary. There have been extensive research along this line. So at the end, let me spend like 1 minute to introduce our lab. Professor Ricardo Hiersen actually mentioned we are Center for Computational Evolutionary Intelligence Lab. And as I mentioned, we tend to build in vertical hierarchies and from circuits to architecture to algorithm level solutions. So we'll be dedicating working on ARM-based designs and the corresponding architecture solutions with the new devices and also conventional platforms. At the algorithm levels in recent years, and we are focusing on compression and acceleration. NAS, new architecture searches and new directions we start exploring. The goal over here is to automate the DNN model designs by integrating constraints and like hardware constraints and for certain applications, and therefore improve the efficiency. So we tend to involve human beings less and less, right? Distributed computing is another line of the research. We aim for very large application with a huge amount of the data and large model size. We also working on like federally learnings and relatively speaking, and the model size is small and the computation can be conducted at the, the training computation and can be conducted at the edge device. In this ways, and individuals and private information will not pass to the center and can be maintained very well. Okay, so this actually concludes my talk today. Again, thank you very much for attending this talk. I just give a very brief introduction on those research. We actually have more studies and behind this, and feel free to reach out to me by emails if any questions. Thanks again.
So thank you very much, Helen. Very nice and inspiring talk. Also very nice gardens in Duke campus.
So, I hope once the situation is getting better, and welcome to visit us.
Yeah, it would be great. So please, we are waiting for questions. So you can do your questions using the YouTube chat channel. Also, we invite all you to subscribe to the IEEE CASS Rio Grande do Sul YouTube channel if you have not done it yet. We have now more than 1,300 people subscribing to the channel. So if you want to do any question, please do it as soon as possible. So I have, to start, I have one question to Helen. So you have shown several approaches to do acceleration. And what is the consequence on power consumption for these approaches?
Yeah, that's a very good question. And I didn't particularly mention about the power consumptions and in this talk, but it is always evaluated in our research, majorly because of my hardware background, I guess. And So when we, for example, when we do the compression works, specifications and prunings, and reduce the computation cost, as you can imagine, the processing time is less, and the used computation and the memory resources is also reduced, and therefore the power consumptions can be reduced. It's not like a proportional relations. For example, when we remove 90% of the computations, and perhaps the power consumptions reduce in 80%. So it's still kind of an it's not like reduced as significant as the parameter numbers, but generally speaking, the saving is pretty large.
Yeah, and another question related to this is what is the change considering the amount of components, like transistors, considering traditional approach?
Okay, so for my first part and talking about the conventional platforms, and that's basically saying that's deploy this on conventional platforms. So there's not much change on the GPU designs, for example. It's just made it run faster. But we have another research like implemented on FPGAs, right? So with those and FPGA implementations, and it can dramatically say the reductions. So in terms of the utilization on the FPGAs. So one of the recent work is talking about the radar signal processing by using DNN and implement on FPGAs, and we can see that for that particular examples, and we save 70% of design cost before and after applying our sparsification technique. Okay, and this is actually a very good question, because this is related to our motivation of ARM-based designs. For ARM-based designs, particularly spike-based designs, okay, the matrix multiplication will be conducted by ARM crossbar array instead of the multiplier. So you can imagine, the design complexity can be dramatically reduced. It's not like only 80% of savings. It's easily can claim as in like 90% or even higher, savings. Yeah.
Thank you. So we have a question by Professor Sergio Bumpi. How do you compensate for large variations of the ReRAM R high to high low to high high variations from chip to chip with the TA02 base memory stores?
Wow.
Do you have a tuning on your op-amps feedback?
Wow. This is a very, very good question. In fact, I assume you perhaps look into this in very detail and know the problem. I talk about our group being working on this for 10 years, especially at the early stage. The variation defect are so tremendous, and we couldn't bypass this problem at all. So back to the variations questions, okay. In our works, we actually include the variation consideration in algorithm training. We also, as you said, tune our Apple circuits. For example, we tune the VRAF and the VRAF and also the threshold voltage, basically for every IFC designs in our test chip. This is mainly because of this variations. We recently also talking about the can we redo this in software and hardware co-designs in order to accommodate the variation during the operation, for example, due to the thermal. Our original resistance level is 500 kiloohms, and for example, during operations, it could fluctuate slightly. So for one devices, it wasn't a big problems, but the computation kind of, for example, in one columns, we could have 100 or 1,000 cells, and then the cumulative effect is pretty significant. So we actually redesign the training and also testing schemes in order to accommodate this. The testing scheme over here is basically after the programming, and we giving certain patterns and to test and to accesses and how much variations per column. And then we tune the Apple circuits.
Okay. Thank you very much, Helen. So I don't see any more questions here. No, there is another by Bumpy also. Do you do online runtime adjustment on FREF and threshold voltage? This would be a way to compensate at runtime for these tremendous memory store variations. It is a complex problem indeed.
Yeah, it is a complex problem. So to answer that quickly, for the chips I just presented, we didn't do runtime adjustment. We basically calibrated every IFC offline and then put them together. Okay. We currently have some online training work. It has to be, I mean, the threshold, the reference and threshold voltage training or the tunings and has to be related or integrated with the crossbar array online training. So we do have an ongoing study on this direction. And I mean, if you're interested, we can talk more about this. We also have some preliminary results on this, but haven't completed work yet.
So another question by Lucilade Dantas. So the training process is also done on a specialized hardware architecture?
So for example, the CMOS part, like CPU and GPUs, we don't have to worry about this. Okay. For ARM-based designs, the short answer is yes. The training process, and for example, I mentioned the curve of an output spike generation versus input my computations, and I show you like there's kind of a fluctuations in the spike generation, right? So those kind of specific to the hardware. In fact, it's very related to the chip by chip basically, and then we integrate such kind of a variation into our training process. Indeed, yes.
Thank you very much. So thank you again, Helen, for this very nice talk.
Thank you.
So bye-bye. See you next week.
Bye-bye.